Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Synopsys with Solaiman Rahim. We're going to talk today about speeding up design closure. Solaiman, designs are getting much more complex. What's happening on the design closure side? What's the impact of all this complexity?
ECO is becoming more and more critical for design closure. As the design complexity and at lower technology node increases, you need to model more advanced physical effect like crosstalk, higher voltage node, hybrid row, LLE, and so on. This make the design closure much more difficult these days.
You're talking about things like noise too, right? I mean, things that you don't necessarily pick up the first time you're going through these designs.
Yes, correct. So noise is also becoming important because you have this double switching effect and you need to be able to catch them and do ECOs on them as well.
Let's take a closer look.
Sure, Ed.
Why is it so important for ECOs to have context of what's going on within a design?
ECOs are typically done post PNR, and it's very important for ECOs to be done in the sign of context. Why? Because ECOs is the process of analyzing timing violation and identifying the change that will be able to fix all of them at the lower power cost. Now, to do that, you need to be in the sign of context because you need the most accurate timing data, power data to drive your ECOs. And this is why having sign of knowledge is very important. The other aspects, especially when you go to the lower technology node, you need to be able to model silicon variation, right? And to model the silicon variation, again, you need to be in the sign of context to be able to model properly the crosstalk, the robustness ECOs, and so on. It's the sensitivity as well. So you can do ECO for those physical effects as well.
What sort of variables are you actually working with here?
Yeah, so one, when you do ECO, you need to do it in the context of obviously very large designs, but also for all the scenarios. And typically you can have up to 100 sign-off scenarios for which you have to do ECOs. And on top of that, when you go to do ECO for multi-die or 3D IC system, the number of corner, there is an explosion of the number of corners. So doing ECO for that number of corners also become problematic. The other also variation that come into the picture, especially for 3D IC, is the thermal effect on those multi-die system. And how do you model them during ECO so you can do the proper ECO? As you know, for 3D ICs, they are stacking multiple die together and they are putting the power delivery network on the top of the die, which create a lot of thermal issue across the system. And if you're not modeling those, you might not get the accurate timing, the accurate airdrop, the accurate power. That might lead to for you to not do the correct ECOs.
And you're also getting issues such as, is this thing going to age well? Will it be reliable out in the marketplace, right?
Correct. So aging is very important because as the chip evolve and then over the time, you might see, power issue, performance issue, and so on. Modeling aging is very important, and that's why it's very important to do ECO in a sign-off platform, so you can actually model aging in your timing, in your power, and so on. So when you do ECO, you are aware of the aging effects. On top of that, you need the ECO also inside the ECO loop to be based on incremental sign-off analysis as well, to be able to take into account those aging effect or variation effect and so on, basically.
You've got a lot more variables in here that used to be handled by the fab in the past. Now it's being pushed left. It's basically the whole shift left, but it's you don't have the margin to be able to play with in order to fix these problems like you did in the past. So now it's much more important to deal with this right in the ECO as opposed to, oh, this can go to the foundry and we can fix it later on.
Correct, Ed. What we see today, right, is a race between our customer to achieve the best performance, power, area for our chip. At the same time, that race, it's also in the foundry side because you also want to guarantee the highest yield. But combining both, we really need ECO to come into the picture to be able to close power, performance, area, and reliability as soon as possible to guarantee to meet the competitiveness of our customer and also the yield of our foundry partners.
Typically, though, when you make changes, you want them to be done as early as possible. It's cheaper, it's more effective, and it's just going to be a lot easier to do it there. How far back now does ECO get pushed to the front?
Yeah, so we can see at ECU a different level of abstraction. There is ECUs even today starting at the system level, right? And at the system level, basically, they are looking at data from previous generation of silicon and try to architect the system based on those data. Then you go to the next of abstraction, RTL. And RTL, there is, RTL ECOs happening every day, which are around improving the clock gating or improving the memory access rate. And then when you go lower to the implementation, post-PNR, this is where you can actually do the most accurate ECOs because you have completed your PNR and you are in the sign-off stage. So getting accurate sign-off, timing data, power data, and so on, this is where you have them, and that's where you can take the best approach for your ECOs. And also your ECO has to be fully physical aware and be aware of all the foundry physical rules as well, so you can do it accurately.
So are the teams that deal with the ECO now different than they were in the past?
So the team who are dealing with the ECOs are still the design team. The designers are using our tools to do the ECOs, the CAD team supporting them, but typically the ECOs are done by the designer themselves, the backend designers using EDA solutions.
These are incredibly complex chips. Can it all be done with tools that exist today? Does it have to be done on the desktop in the local server farms, or does it now have to be pushed into the cloud?
Typically, a design comes with many, many blocks, right? So you have to do ECO for many, many blocks. You have to do ECO for the subsystem. You have to do ECO for the full chip. And that's why you need to really distribute the ECO. You cannot do it sequentially. You have to do the ECO for all the blocks, the interface ECOs, the full chip ECOs, all in parallel. So that requires a lot of compute. The ECO is really, really good for cloud. This is where you have to do your ECOs because you really need a lot of machine and distribute all these different ECOs for all the blocks, for the full chip, for the subsystem, all together. The other things that you need in ECO is you want your ECO to be single box. And by single box, what I mean is like your ECO should be able to use MCMM technology, multi-corner, multi-mode technology, to be able to take hundreds of scenarios and do the ECO for 100 scenario on a single machine. And why you need to do that? Because you need to do ECO for many, many blocks. And if you want to do it in the cloud, you need this to be single box, so you lower your cost per node when you go to the cloud.
Are the tools for ECO keeping up with the problems that are arising?
Historically, ECO was for timing, right? And it has been constantly enhanced to take into account other aspects. So first, recovering power, right? Swapping the VTs. But also, as you go to the lower technology node, you are looking at much more IR drop. Yeah? The IR drop effect grow exponentially at 3 nanometer. So you need to do ECOs for IR drop as well. And now that you go to the lowest technology node, there's a lot of other effects that happen in the silicon that you need to model properly and be able to do ECO on them. And what we see in the industry is that the ECO tools are keeping up, and they are actually able to do obviously timing fixing, power recovery, IR drop fixing, but also be able to model the sensitivity in the silicon and bring them during the ECO. So when you do the ECO, you take into account those effects that happen in the silicon and do the ECO properly, so you can fix issues that you could have seen in the silicon.
How about heterogeneous integration, chiplets, things like that? Does it cause more problems on the ECO side?
Yeah, because on the interface, you need to do the proper ECOs. And what happened is like when you do your block level, you typically do your block level separately from your chip. And the interface path, you might not apply the right ECO for the inside the block to the outside of the block. So having very, very good interface fixing ECOs is very important.
How are you measuring that? And how do you gauge when something needs to be fixed on an ECO? Because is there better visibility now into what's going on inside the chip?
Yeah, so the one thing is to be able to see the full chip. And this is why you need a single box solution built on top of really for scenario. We can actually load the entire SoC, right? And be able to do flat ECO for hundreds of scenarios. So having technology to be able to load the entire chip, be able to look at the entire block to chip path as well, and look at all the scenarios is very important in ECO.
So this is both a combination of simulation as well as pathfinding, right?
So it's really a combination of simulation and pathfinding. And I think ECO, like you need to be able first to run timing and do timing for the entire chip and find where are all the violating paths, and then be able to consume those violating paths in your ECO and do the ECO on those violating paths at the lower power cost, right? And then the other aspect is power, because opportunity to reduce power can happen everywhere in the design, not only on the violating timing path. So be able to load the entire design and find area where you can recover power is also very important.
How much do you have to worry about things like variation on the manufacturing processes as well? Because that's becoming more difficult as we get down into 5 nanometer, 3 nanometer.
Yeah, so this is a very good question. We have partnered with our foundry team, and we have a solution at Synopsys where we have worked with them to model those variations in our tool. And we have built specific ML model based on those variations that we see based on the foundry data. And all our tools now are able to consume those information and take into account the variation. It's not only for ECO. Actually, the entire tool set in our company is able now to take into account, from implementation to sign off and to physical verification.
AI come in here as well? Is there any use of AI machine learning?
Yeah, so ECO is a concept of coming with the best possible recipe to close timing at the lower power cost. When you do ECO, you have potentially millions of different ways of doing an ECO. How to find the fastest way, the best possible recipe, this is where you can use AI to identify the best recipe for ECOs. The other area where you can use AI is for the last mile. So for the last mile, basically what happens is tool today can close potentially 99% of your validating paths, but you cannot tape out without closing all of them. So today, designers goes and manually try to fix those paths. But we can use ML and AI to learn from what they have been doing and then integrate that in our solution. So this is where also you can use AI and ML technology. And then finally, also what is important is on the GUI side, you need to have very, very strong GUI where you can overlay all the layout, the physical information, the timing information for the designer to be able to identify what are the best manual ECO they can do. And from that GUI, now you can use AI also to learn from what they have been doing and integrate that in your solution.
The margin that you used to have in these designs has pretty much disappeared. Does that make finding the ECOs more important and more difficult?
Yes, people still do use margin. It's not they didn't completely disappear, but it become very difficult to play on the margin. But just to give an example, right? So when you do, for example, all fixing, right? And you're trying to do all fixing, but you don't have any setup margin, right? So you cannot close all because you don't have any setup margin. So what you do is like you go and create some setup margin, right? And then you fix by creating the setup margin, you can now go and fix the old, right? So when you do ECO, you actually need to play yourself with the margins to open margin somewhere to be able to close something else somewhere else. And those kind of tricks are very important in the ECOs.
How much of this can be run in parallel and how much does that help?
Yeah, so as I mentioned, running ECO for all the block in parallel is very important. And what you need to also to do is to do the ECO for the subsystem and the full chip in parallel of those blocks, right? So you need to concurrently optimize the chip and the block together. So this CCO, which is chiplet block co-optimization, is very important. And that is something you need to integrate as part of your implementation solution as well.
So you need a lot of cycles to be able to run this, right?
You need a lot of cycle and you need a lot of compute. And this is where having a single box solution is very important because now you can reduce your hardware cost and then be able to do all this in parallel. And the whole goal of ECO is productivity. ECO typically take a month in the design cycle. How can I reduce this month to a week so I can close faster and gain productivity? And be able to do everything in parallel is very important. Be able to do chiplet block optimization become very important. And doing it as early as possible as PNR become even more important.
Solaiman Rahim, thanks for a great explanation.
Thank you, Ed.